Hi guys, so it's Mrs. Avila here, and today I'm going to be helping you guys with 11.1, which is our introduction to probability. If you have not already gone on Google Classroom and accessed the notes for 11.1, I would encourage you to pause the video now and do so that you can follow along with our instruction. All right, now once you have those along with a pen or a pencil, I'm going to suggest, there we go. All right. We are going to work our way through this, and I am going to start off with this idea of something called the fundamental counting principle. All right, now I'm going to go ahead and close out this little webcam window so I can get right to it. All right, so solving problems involving the fundamental counting principle versus solving problems involving permutations and combinations, it just depends on the type of problem that you're looking at. Let's start out with this fundamental counting principle. The fundamental counting principle basically is a way to help figure out how many different ways something or a series of things can occur so that you can then use that amount of options to your advantage when finding probability. Let's start off with example 1. For the lunch special, you can choose an entree, a drink, and one side dish. How many meal choices are there in total? The fundamental counting principle says that if there's a total of n items, and there's a certain amount of ways that you could choose each set of the items, you could, and what's kind of hidden back here, you can take those amount of options and just multiply them to get the total number of combinations. So for this one, if we want to know how many total meal options, one option would be to actually write out all the different combinations. So I could write pizza with salad, and I could say milk. That would be one option, but then I would have to do every other combination, and that could involve things like pizza, salad, and all of a sudden I throw punch in there, and that is a second combination. So this could actually take a while, and I don't want to necessarily list them all out. So instead, I'm going to take the fact that there are 3 possible entree options, there's 3 possible side dish options, and then there's 4 possible drink options. To figure out my total number of combinations, I can simply do 3 times 3 times 4. And if I do that, I'm going to get a total of 36 combinations. Okay. So that's how our fundamental counting principle works. All right. So let's try a couple practice problems. Take a moment, pause this video, and try and figure out the answers for practice 1 and practice 2. When you've had a chance to try it, you can go ahead, press play, and look at the answers. All right. So for this one, I'm going to switch up my color. Number 1 says, make your own adventure story, lets you choose 6 starting points, gives 4 plot choices, and then 5 possible endings. How many adventures are there? So being that there's 6 starting, 4 plot, and 5 possible endings, I can simply go 6 times 4 times 5, and that's going to get me a total of 120 adventures. A password has 4 letters followed by 1 digit. Uppercase A and lowercase a may be used and are considered different. How many passwords are possible? Okay, well, how many letters are in the alphabet? There's actually 26 letters in the alphabet, which means if uppercase and lowercase are considered different, that would mean there are 52 letters total to choose from. So I'm going to break this down. I'm going to say I have 1, 2, 3, 4, and then 5. This is my number. There's a total of 52 options for this first spot of the password, which would be a letter. They don't in any way indicate that I can't use letters again. So I'm going to say that there's still 52 options for each of these next spots. And then I get to this end and I can have to pick 1 digit. Digits there's actually 10 single digits, 0 through 9. A lot of people forget about 0. So if I multiply all of these out, I'm going to get 73,116,160 total password options. Now, granted, this problem didn't ask you for this, but one thing that you could do if you needed to adjust this is what if the problem said no repeats? If it said no repeats, I would still multiply to get my total number of options. But if I couldn't repeat that first letter, it would mean there would only be 51 options, and then 50, and then 49. There would only be 64,974,000 passwords if there was no repeats. All right. So that's our fundamental counting principle. Really nice to figure out how many different ways something can happen or a combination of things can happen when you're looking at like a series of decisions or a series of things happening. So let's shift our attention. So for this question, it says, does order matter? A book club offers a choice of 8 books from a list of 40. How many different collections can a member make? Versus the question, in a race in which 6 automobiles are entered and there are not ties, in how many ways can the first 4 finishers come in? So a lot of times when people look at questions like this, one of the things I want you guys to start thinking about is, does order matter? Okay, so with number 1, a book club offers a choice of 8 books from a list of 40. If I pick 8 books and then I were to swap the first book and the last book in terms of the 8 that I selected, would that be considered a different collection of books? Not really. I'd still be reading the same 8 books. Versus number 2, if I'm looking at how many ways the first 4 finishers can come in, if I have a first place, a second place, a third place, and then a fourth place, and I take the first place finisher and the fourth place finisher and I swap them, would that count as a different way that the finishers could come in? Absolutely. Order would matter in this one. All right. So that brings us to our idea of permutations versus combinations. Permutations and combinations are very, very similar and, in fact, calculated very similarly, but one of them order matters for and one of them order does not. Okay, I give the example of a fruit salad. A fruit salad is a combination of apples, grapes, and bananas. We call it a combination because we really don't care the order that the fruits are put into the salad. Okay, if I put bananas, grapes, and apples versus grapes, apples, and bananas, it really is the same fruit salad, especially when I mix them all up. Okay. However, a lot of times people use the word combination incorrectly when talking about passwords or locks. This says a combination to the safe was 472. In this case, we do care about the order. 472 would not work, 42724 would not work, nor would 247. This I like to associate with your idea of your PE lockers. If you go to your PE locker and you have one of those 3-digit combination locks that you circle, that is going to only work if you put the 3 numbers in that particular order. Okay, so one way to remember the difference between permutation and combinations is combination locks that you use in PE should actually be called permutation locks because the order of the numbers matter. So if we can tell the difference between whether something would be a permutation or combination, how can we calculate the total number of ways that something could happen? Well, I like to tell people to look for some keywords. Okay, so for permutations, some keywords to look for, but not limited to, are things like if things are getting arranged or displayed or put in order or lined up. Those are all words or phrases that help indicate that the order of the things is going to matter, meaning if I switch the first and the last one, that would be considered a new arrangement or a new display or a new order. Okay. How to calculate the total number of ways that a permutation can occur is I need to know 2 things. I need to know the total number of items and the number of the items that are being selected and then put in this particular order. This is going to be our formula right here for our permutation. Now, if you haven't at this point gone back and done the review about factorials, you might want to go back and take a look at that. I'll talk about it a little bit here, but we had some review work earlier in the agenda that you might want to take a look at. So let's say I have a total of 5 things that I'm picking, and I am selecting 3 out of the 5. There we go. I can use this formula. My n in this case would be the 5, my r would be the 3. So when I do 5 factorial, with a little exclamation mark, and then I do 5 minus 3 factorial in the bottom. Factorial, all that means is that you're going to multiply everything from that number and everything before it. So let's say I had 8 factorial. 8 factorial would be like doing 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so 5 factorial is 5 times 4 times 3 times 2 times 1. 5 minus 3 is just 2 factorial, so that's where 2 times 1 came in. And when I simplify that, I get a total of 60. So if I have 5 items and I'm picking 3 of them and the order does matter, there's going to be 60 ways for that to occur. Combinations are similar but a little bit different. Combinations you calculate in a very similar fashion. You have a certain amount of things, and you're choosing r numbers of them. Okay, so same idea, 5 and 3. But for combinations, you use a slightly different formula where you have this extra little r factorial out in front in the denominator. Okay, this formula is used if the order does not matter, meaning if I select 4 things and I switch the first and the last one, but really that 4 things that all clumped together would count as the exact same thing regardless of the order they were in. That would be considered a combination. If you're ever being asked to simply select or collect or pick things, unless otherwise indicated that order is important, those typically have order not matter. All right, so 5 combination 3, very similar situation. I'm going to do 5 factorial on the top. On the bottom, I'm going to have that extra r factorial, so 3 factorial times, this is going to turn into 2 factorial right here. So I can either multiply and then simplify, or I could even just simplify if I wanted to before I multiplied. That would turn into 5 times 4 over 2, which in fact that is 20 divided by 2, which was 10. I do want to point out, if you like this idea of crossing out the matching terms on the top and bottom, don't cross out every number that you see. Notice that in this particular case, I simplified the 2 on top and the 2 on bottom, but I couldn't then cross out all 2's everywhere. I could only cross out pairs on top and bottom that matched. All right, so let's try and calculate using these formulas. You can expand out with factorials and then simplify, or you can multiply and simplify at the end. It's totally up to you, but pause the video now and try these. All right, so now that you have a chance to check these, let's take a look. So for combination 2, that means I'm going to use this formula right here. So I'm going to do 4 factorial over, I'm going to do 2 factorial times 4 minus 2 factorial. That turns into 4 factorial over 2 factorial times 2 factorial. And expand this out. I have 4 times 3 times 2 times 1. I have 2 times 1 times 2 times 1. I'm only going to cross out things that match on top and bottom in pairs. So I get 12 over 2, which is just 6. This one I'm going to do a permutation. Same idea, except I'm not going to have that extra r factorial. So I'm going to have 4 factorial over 4 minus 2 factorial. So from our previous problem, we can see 4 times 3 times 2 times 1 over 2 times 1. I'm still going to cross out my 2's and my 1's, but notice in this case, all I have left at this point is 12. So there's more ways to select 2 things out of 4 if the order makes a difference. Use my combination formula. So I'm going to have 5 factorial over 1 factorial, which is just 1, and then that's going to be 5 minus 1 factorial. So I'm going to get 5 times 4 times 3 times 2 times 1 over 1 times 5 minus 1 is 4 factorial, so that's 4 times 3 times 2 times 1. Again, I'm going to cross out the parts that match. So I have a 1, a 1, a 2, a 2, a 3, 3, 4, 4. Everything crosses out, simplifies except the 5 and the 1. So my answer in this case is just 5 over 1, which is just 5. All right, and last but not least, we have another permutation. So over here, so I'm going to do 3 factorial over 3 minus 3 factorial. All right, so 3 factorial is 3 times 2 times 1. 3 minus 3 is 0 factorial. And a lot of people have a hard time with this one, but 0 factorial is kind of one of those weird numbers, very similar to, if you think about it, if you ever have done a number, let's say 3 raised to the 0 power, what do you get back? Yeah, you get back a 1, right? In fact, if you have x to the 0 power, what do you get back? Exactly, you get back a 1, right? So 0 factorial is one of those strange things where you get back actually a 1 from 0 factorial. Try punching it in your calculator and you'll see. So I really get 3 times 2 times 1, which is 6, over 1, so my answer would just be 6. All right, so we know how to calculate permutations and combinations. Now we need to gauge whether or not we can tell the difference between them. Okay, so let's say for these 5 scenarios, I want you to read them and I want you to try and just next to each one identify whether you think it'd be a permutation or a combination, and then you can check your answers in just a second. All right, so number 5, Nathan has a dozen eggs. Okay, and he wants to decorate 4 eggs for an art project. So the question is, so we want to decorate 4 eggs. We're trying to figure out, does it matter the order that he decorates them? Okay, so if I pick 4 eggs, so let's say I pick egg 1, 2, 3, 4. Those are the 4 eggs that I pick out of, let's say, the 12 total eggs that I have. If I swap this first egg and this 4th egg, does that change which eggs I'm decorating? No. The answer is no. So I would say that this is going to be a combination. Okay. However, number 6, Mr. Gunther, he's lining up 12 kids from his kindergarten class for a performance. Remember, lining up or displaying or arranging, those are all some of our keywords to indicate that this would be a permutation. If I take the first kid in line and the last kid in line and I swap them, that would be a different order of students. That would be a new line. All right, number 7, Rachel has 10 valuable baseball cards. She wants to select 2 of them to sell online. This would be a combination. Select was one of our keywords to indicate we don't really care the order of the 2 cards. We just want to know which 2 cards in general get picked to be sold. Don has 5 soccer trophies lined up on the mantle of his fireplace, so he's displaying these 5 soccer trophies. That would indicate that I do care about the order in terms of the arrangement and how it looks. And number 9, Bree has to select 5 photos from a box containing 25 photos to use in the yearbook. It says to use. It's not talking about displaying or arranging them any particular way. If it did, I would change my answer, but based on what's told here, I'm going to say this is just a combination. All right, so let's try and put it all together. Okay, so this says there are 12 different colored cubes in a bag. How many ways can Randall draw a set of 4 cubes from the bag one at a time? So step 1 is I need to figure out whether the problem represents a permutation or a combination. Okay, so I'm picking 4 cubes from the bag, and I'm trying to just figure out which 4 are going to be selected. So in this case, I'm going to say a combination. Sorry, that's terrible. A combination, because I'm just looking for which 4 are being selected. It's not talking about lining them up or putting them in order or arranging them, displaying them. So I'm just going to say a combination here. And so now it says I'm going to use the formula. I'm going to use the formula in this case 12 combination 4. And that formula is going to be this one right up here. Okay, so in this case, I would do 12 factorial over 4 factorial times 12 minus 4 factorial. That would be my formula I'm going to use here. So let's go ahead and simplify that. So I have this 12 minus 4 really turns into just an 8 factorial. So I can do this a couple ways. One way is I can actually expand it all out. I can do 12 times 11 times 10 times 9 times 8 times 7 times 6, etc. all the way down. And I can do that with my 4 times my 3 times my 2 times my 1. And then I could do that with my 8 times my 7 times my 6 times my 5. All right, I can do that. And then if I have that all written out, I can go ahead and I can simplify a bunch of these things. Right? I could have also just recognized that 8 factorial would be included in the 8 and the 12. So if I wanted to at this point, I could have just said 12 times 11 times 10 times 9 times 8 factorial. And then I could have said 4 times 3 times 2 times 1 times 8 factorial. Then I could have just crossed those out without having to take the time to expand them all out. Now, it turns out this is actually a pretty big number of ways. In fact, it's 495 ways. Now we have a couple U-tries for you to take a look at. Again, pause the video and then come back and you can take a look. All right, so this says in a conference of 9 schools, how many football games are played during the season if the teams all play each other exactly once? Does order matter? So if I pick Granada and Livermore to play each other, does it matter if I pick Granada first and they play Livermore, or Livermore first and they play Granada? Not necessarily. Okay, it's the same 2 teams that are being played. So I'm going to say this is a combination. My N in this case is there's 9 schools, and I'm picking any 2 of them at a time to play each other. So I'm going to go 9 combination 2. That's going to give me 9 factorial over 2 factorial times 7 factorial, because I did the 9 minus 2. That's going to give me 9 times 8 times 7 factorial over 2 times 1 times 7 factorial. I can cross out my 7 factorials, and I'm going to get 36. Let's look at number 2. You're going to draw 4 cards from a standard deck of 52. How many different 4-card hands are possible? We're being asked, does order matter? If I have a Jack, Queen, King, Ace in my hand, does it matter if I swap the King and the Ace in terms of the order they're in my hand? No, it would be the exact same 4 cards. So it's a combination. I'm choosing from 52 cards, and I'm picking 4 at a time. So I'm going to go 52 combination 4. That's 52 factorial over 4 factorial times 52 minus 4 factorial. Again, I don't want to have to write all these out, so I'm going to notice that this right here is actually going to be 48 factorial, so I'm only going to expand out I'm only going to expand out that numerator to 49, and then I'm just going to write 48 factorial here so that I can just simplify. And there are 270,725 ways to get any four cards out of a deck of 52. All right, and let's wrap it up. This will be our last one. It says 6 different books will be displayed in the library window. How many different arrangements are there? There are 2 keywords here. We're talking about displaying and then arranging them in the window. Right away, my ears perk up, and I'm going to say permutation. I'm picking 6, and I'm displaying all 6. So this is a 6 permutation 6 option. That's going to be 6 factorial over 6 minus 6 factorial. So I get 6 times 5 times 4 times 3 times 2 times 1 over 6 minus 6. Remember, this is 0 factorial, which is just 1. So that's going to give me 720 different ways you can display 6 books in a library window. All right, I hope that helped in terms of your calculations and differentiating permutations versus combinations. Remember, the fundamental counting principle is used when you are making a series of decisions. For example, the lunch special or combining different parts of a story. Go ahead, take a look at your 11.1 practice, try it out, and then shoot any questions that you have for us our way.